Let's jump right into this explainer on the structural stereoselectivity and tautomeric dynamics of histamine. Now, you probably know histamine as that annoying chemical culprit behind your seasonal sniffles and itchy eyes, right? But it's actually the ultimate microscopic master of disguise. We're going to unpack exactly how this incredible system operates, and trust me, you'll walk away with a whole new appreciation for the microscopic gymnastics happening inside your body right now.
Because here's the big question. How does one seemingly shapeless molecule manage to unlock so many highly specific doors in our body? It's a massive biological mystery how a single chemical can juggle so many different jobs. I mean, it regulates stomach acid, acts as a neurotransmitter in your brain, and, yeah, kicks off your immune responses. The answer to how it pulls off this incredibly diverse resume? It lies entirely in its ability to shapeshift.
Which brings us to our first section, meet the shapeshifter.
See, before it even binds to a cell or triggers a single sneeze, histamine operates without a fixed identity. By itself, it's an achiral molecule. In chemistry, that means it completely lacks a specific, rigid 3D shape or fixed-handedness. It's not locked into being right-handed or left-handed. Instead, it's just kind of floating around your system like a highly trained spy waiting for a mission, totally fluid, flexible, and completely ready to adapt. So let's move into our next section, picky receptors in our flexible molecule.
How exactly does this super laid-back, formless molecule interact with the VIP doors of our body, the cellular receptors? Well, the magic word here is stereoselectivity. You see, our cellular receptors are absolute divas. While histamine is cool just floating around shapeless, the receptors themselves actually demand chiral ligands to fit perfectly. They're strict biological lock-and-key mechanisms that absolutely require a very specific, rigid, three-dimensional key. So how does our shapeless little spy get past these incredibly demanding cellular bouncers?
It literally bends its physical shape on demand. When histamine wants to unlock, say, the H1 receptors that cause your allergies, or the H2 receptors managing your stomach acid, it morphs into what chemists call a trans shape. But if it needs to talk to the H3 receptors in your nervous system, it twists itself entirely into a gauche shape. It is the exact same molecule, just physically folded in completely different ways to satisfy the crazy demands of those different cellular locks.
All right, moving right along to section 3, tautomers and the proton shuffle.
Because histamine doesn't just bend its body, it literally rearranges its chemical armor in real time, and it does this through tautomers. Tautomers are basically the exact same molecule constantly swapping its molecular hats. They're rapidly interconverting forms that differ only in the position of a single H+ proton. Imagine a molecule just rapidly passing a baton back and forth across its own structure. That dynamic, continuous, high-speed shifting, that is tautomerization in a nutshell. Which naturally leads us to section 4, survival at physiological pH. To really get this proton shuffle, we gotta look at the real-world environment of the human body, which is heavily dictated by pH. Right at our natural physiological pH of 7.4, the healthy baseline for human blood and tissue, a whopping 96.6% of histamine exists as the monocationic conjugate species. Chemically, we label that as NH3+. Out of all the possible forms it could take, nature has perfectly optimized histamine so that almost all of it settles right into this exact electrical state to function beautifully. But as we know, our bodies aren't just one perfectly uniform environment. If the local area changes and the pH drops down, becoming more acidic, histamine instantly responds. It adapts on the fly by shifting into a higher percentage of the dicaionic species. Basically, the molecule is dynamically changing its own electrical charge profile entirely based on the acidity of the fluid swimming around it. How cool is that? Now, if we look back at that dominant monocation species we were just talking about, the molecule actually divides its proton shuffling forms with mathematical precision. Exactly 80% takes the N-tau-H form, while the other 20% acts as the N-pi-H form. It's this incredibly stable, predictable demographic split, and it's happening at a microscopic level literally millions of times every single second. Let's bring it all home with our final section, the pharmacophore conclusion. When we put all these moving parts together, it becomes super clear why these microscopic shapeshifts matter so much for biology and medicine. Really detailed structure-activity relationship studies have proven that the alpha NH3+ monocation is the absolute master key to turning on these receptors. It creates that agonist activity, the literal spark that kicks off the biological reaction. And if we zoom in even closer, that dominant 80% N-tau-H tautomer we just mentioned, that serves as the ultimate pharmacophoric key. It is the exact specific active form required to successfully unlock the H1 receptor. So I'll leave you with this to ponder. If we can truly master the chemical disguises of molecules like histamine, if we can precisely map out how they fold from trans to gauche and how they shuffle their protons at different pH levels, what incredible, highly targeted medicines could we design next? When we stop looking at molecules as just static, flat drawings in a textbook and start treating them like the dynamic, adapting shapeshifters they really are, the potential to create life-changing therapeutics with virtually no side effects, well, it's absolutely boundless.